Solar flares are not just natural phenomena. They're revealing a truth that has long been overlooked. These sudden bursts of magnetic energy supercharge Earth's upper atmosphere, disrupt radio signals, and threaten satellites and astronauts. Over decades, scientists have known flare plasma, https www.earth.com/news. Super high-resolution solar flare images reveal the sun's hidden magnetic forces gets incredibly hot. But exactly how different particles heat up, and why certain spectral fingerprints look too wide, has remained a nagging mystery since the 1970s. A new study led by Alexander Russell at the University of St. Andrews, https www.standrews.ac.uk, offers a clean, intuitive answer. During key phases of a flare, ions are far hotter than electrons. Not just a little hotter, about 6.5 times hotter, with ion temperatures likely exceeding 60 million degrees Kelvin. This shift in perspective neatly explains why many flare emission lines appear broader than expected, without needing to invoke large, persistent turbulence. Significance of hotter ions. Solar plasma is a soup of charged particles, lightweight electrons and heavier ions, like iron, calcium, and other elements. Historically, many models assumed electrons and ions quickly share energy and settle to a common temperature. This assumption made the math tidy, but it may not reflect reality during a flare's most dynamic moments. Russell's team revisited basic heating physics in flares and drew on growing evidence from near-Earth space plasmas. Hot ions and solar flares. Across the solar wind and near-Earth space, a process called magnetic reconnection, where stressed magnetic field lines snap and rapidly rejoin, is observed to heat ions 6.5 times as much as electrons, following a surprisingly consistent ratio. We were excited by recent discoveries that a process called magnetic reconnection heats ions 6.5 times as much as electrons, Russell explained. This appears to be a universal law, confirmed in near-Earth space, the solar wind, and computer simulations. However, nobody had previously connected work in those fields to solar flares. Carry that rule of thumb to the sun, and you get a dramatic, testable prediction. Early in a flare, and high above the bright loop of hot plasma, the ion temperature can soar past 60 million K, remaining much higher than the electron temperature for tens of minutes. This temperature split matters because it changes how telescopes interpret what they see. Spectral lines, bright features at ultraviolet and X-ray wavelengths, are wider when emitting them are hotter and moving faster. For nearly 50 years, too wide lines were usually blamed on unresolved turbulent motions. The new work suggests superhot ions could be responsible for a big share of that extra width. Solving an astrophysics mystery. If ions are smoking hot, they jiggle more rapidly, and the light they emit spreads over a wider range of wavelengths. This broadening can look exactly like turbulence, which led to decades of debate about what physically stirred flare plasma so vigorously. Russell's team lays out why ion-heavy heating at the onset of flares, and in the above-the-loop top region, where reconnection outflows crash into denser plasma, naturally produces the observed line widths. What's more, the new ion temperature fits well with the width of flare spectral lines, potentially solving an astrophysics mystery that has stood for nearly half a century, noted Russell. A key enabler of this explanation is timescale. In dense, cooling loops after a flare brightens, ions and electrons collide often enough to share energy and equalize temperatures relatively quickly. But higher up, where densities are lower, collisions are rarer. That means the ion-electron temperature gap can persist long enough to leave a clear imprint on the flare spectrum. The paper argues that past estimates of equilibration were often based on the dense loop conditions, not the more rarefied, earlier or higher regions where reconnection does its fiercest work. Past and future observations. The elegance of the proposal is that it doesn't require radical new physics. It borrows a well-supported heating ratio from reconnection studies in the solar wind and Earth's magnetosphere, and simply applies it where reconnection is strongest on the Sun. The result is a unified picture. Reconnection preferentially energizes ions. Low densities up high, let that temperature advantage survive. And hot ions inflate spectral lines that have long looked non-thermal. If correct, the idea reshapes how researchers interpret past observations and plan future ones. Instruments that separate lines from different ions and compare them with electron-sensitive diagnostics could directly test whether line widths trap the higher ion temperature rather than turbulence. This new concept also encourages modelers to let ions and electrons evolve separately in the crucial early minutes of a flare, instead of forcing them to share a single temperature from the start. Space weather made a bit clearer. This is more than a bookkeeping fix. Space weather forecasts depend on how quickly and how hot flare plasmas get, because the resulting radiation and particle storms determine how much they can disturb Earth's ionosphere and threaten spacecraft. If ions get the lion's share of heat at first, that affects energy transport, shock formation, and particle acceleration, the seeds of the most disruptive events. The study also suggests new observational sweet spots. Look early, when the flare is just switching on. Look above the bright loop tops, where reconnection outflows crash and churn. Furthermore, look at line widths from multiple ions, comparing them with electron temperature diagnostics. If the widths line up with a 6.5 to 1 ion to electron temperature split, that's a powerful fingerprint. A new look at solar flares. Solar physics has long assumed that ions and electrons quickly come to the same temperature in flares. Russell and colleagues show that dropping this assumption, especially during the flare onset and in the high, thin plasma above the loops, solves a stubborn spectral riddle with one straightforward, physically motivated change. Ions are simply much hotter. It's a tidy answer that ties the sun's fiercest moments to a universal reconnection rule measured throughout near-Earth space. And it gives observers and modelers a clear roadmap for cracking open one of heliophysics' longest-running mysteries. Like what you read? Subscribe to our newsletter, https:// for engaging articles, exclusive content, and the latest updates. Check us out on EarthSnap, a free app brought to you by Eric Rawls, an interactive game jar the step to subscribe to the newsletter.